Hello, and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be examining the Gaussian random variable. Alright, Gaussian random variable is one that you're going to encounter quite a bit throughout your career. It's probably the most common probability density function that you'll run into. We use it a lot in electrical systems to describe noise and various other random things that affect our lives as engineers. So I'm going to spend some time looking at the probability density function and cumulative distribution function for the Gaussian random variable and several different formulations. So Gaussian random variable probability density function looks something like this. The probability density function for a general Gaussian random variable looks like this. Okay, that's what that looks like. Let me draw a picture, make some sense of this. All right. This is what a Gaussian random variable's probability density function looks like in general. So this is a general Gaussian PDF. All right. By symmetry, my Gaussian random variable PDF is centered at M. M is known as the mean. We'll have a lot more to say about means and moments and other things a little bit later on, but for now I just need to introduce a few terms. The mean is a special point in any probability density function. The probability that my random variable is greater than or equal to the mean equals the probability that the random variable is less than or equal to the mean, and that's always exactly equal to 1/2. All right, it's 50% likely that my random variable will be above the mean and 50% likely that it will be below the mean. All right, so that's my first parameter. My next parameter in my Gaussian probability density function is sigma. Sigma has a special name. It's known as the standard deviation. Again, standard deviation is a concept that we're going to introduce in much more detail in a much more general way in a few lectures from now. And interestingly enough, if we square the standard deviation, we call it something else. We call it the variance. The variance or the standard deviation both affect the width of my Gaussian probability density function. All right? These two things affect the standard deviation, or the square of the standard deviation known as the variance, both affect the width of the Gaussian probability density function. Now, I've generally sketched in sigma here. I'm not meaning to indicate that sigma is a 1 over e point or a 1 over e squared point or a 50% point or anything like that. This is just a very generic way of demonstrating that sigma affects the width of the Gaussian PDF. I'm not indicating anything other than that now. So please don't take the location of sigma on this curve to mean anything particular. This curve has unit area. As you might imagine, it's a proper probability density function. All proper probability density functions have unit area. It will always be unit area regardless of the mean and standard deviation. All right? Always, 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 always. A Gaussian random variable probability density function will have unit area under the PDF for any mean and standard deviation. Okay. So, that's the easy part. The rest of this video lecture is going to be spent getting access to the cumulative distribution function. And there's lots of ways we're going to represent the CDF. So, the cumulative distribution function, you'll recall, is the integral from minus infinity up to some unspecified level x of a probability density function. Okay? For my Gaussian random variable, I'm going to let u equal x minus m over sigma, and therefore du will be dx over sigma. Plug in my Gaussian random variable probability density function from the previous page, and I get this. I need to make that a little bit bigger. All right, that's that. My integrand now, after doing this change of variables, my integrand is a zero mean unit variance Gaussian probability density function. So the integrand is a zero mean unit variance Gaussian probability density function. All right. What I mean is, I'm going to set my mean to 0 and set sigma, in both cases, equal to 1. That gives me a zero mean unit variance Gaussian probability density function. Okay. Let's take this another step and put it into a form that's fairly common. Pull out my 1 over square root of 2 pi. I'm going to integrate that from minus infinity to plus infinity, e to the minus u squared over 2 du minus integral from x minus m over sigma to plus infinity e to the minus u squared over 2 du. All right. I pulled out my 1 over square root of 2 pi, but if my 1 over square root of 2 pi, if this was back inside there, the integrand of this first integral would once again be my zero mean unit variance Gaussian probability density function, and we know that the area under any Gaussian function is exactly 1. So this turns out to be 1 minus, I'm going to write it this way, integral from alpha to infinity of 1 over square root of 2 pi e to the minus u squared over, let's fix that, let's make that look a little nicer, u squared over 2 du, where alpha equals x minus m over sigma. Okay? All right. Unfortunately, this integral, that integral right there, cannot be simplified further in closed form. Turns out I can't integrate that and get a simpler function. So let's talk about it a bit. I'm going to define a function called a Q function. Q of alpha is 1 over square root of 2 pi, integral from alpha to infinity, e to the minus u squared over 2 du. All right. This is a function. The Q function is something you'll encounter quite often in the electrical engineering world. It seems to be more or less unique to the electrical engineering world. It's not something I typically run into when I'm studying mathematics books that are just for mathematicians. I see it a lot in engineering textbooks when we're talking about the Gaussian function. So what you can see is this is the integral of the upper tail from alpha to infinity. Integral of the upper tail of a zero mean unit variance Gaussian PDF. All right. This, the Q function is tabulated. I believe in your textbooks it is Appendix E. Appendix E. And I've also made available to you 2 programs. One, these are MATLAB programs, Q.M, and I also have made available to you the inverse, QINV.M. These are MATLAB programs. All right, you can run those programs, give it a value alpha, and it'll spit back for you the integral of the upper tail of a zero mean unit variance Gaussian function. All right, very simply then, looking back to my previous page, since we've defined Q as we have at the top of this page, looking back to the previous page, the relationship on the bottom, I can write this down. I can say that for a general Gaussian, my cumulative distribution function is 1 minus this Q function evaluated at x minus m over sigma. All right. That is the CDF for a general That's the cumulative distribution function for a general Gaussian probability density function. Okay? So let me draw a couple of figures here. Let's remind ourselves one over sigma squared at 2 pi e to the minus x minus m squared over 2 sigma squared. That's a general Gaussian PDF. Okay, that's a general Gaussian PDF. Let's make a little picture here. A general Gaussian might look something like this. This is the mean. It's 50% likely to be above the mean, and 50% likely to be below the mean. And the width of my PDF is dictated by the standard deviation or variance. All right, so let's pick some point on my curve here. Let's call that x naught. Okay? The cumulative distribution function is the integral from minus infinity up to x naught. So the area under my curve here, this piece, is the cumulative distribution function evaluated at x naught. The area under the curve that I've hatched in as red is the cumulative distribution function evaluated at x naught. And this, of course, is the integral from minus infinity up to x naught of my PDF. Okay? All right. So let me now draw a zero mean unit variance Gaussian. And we'll call this x prime just to make some make things a little bit different. F let me draw this. And got a 0 up here. Let's call this point x naught prime. Okay? Now the q function is the integral. By the way, you'll notice what I've done here is this function that I've sketched here is a zero mean unit variance. It's centered at 0. It's centered down here at 0. Zero mean unit variance or unit standard deviation Gaussian. Okay? It's a zero mean unit variance Gaussian. The q function, as we've seen just a few minutes ago on the previous slide, is the integral over the upper tail. That's the integral over the upper tail of a zero mean unit variance Gaussian PDF. So this area here is q of x naught prime. Okay? That's q of x naught prime. So then, if x naught prime equals x naught minus m over sigma, then I need some more room here. The cumulative distribution function evaluated at x naught equals 1 minus q of x naught prime, which is 1 minus the q function x naught minus m over sigma. All right? So if you know x naught, you know the mean, you know the variance, you know the standard deviation, calculate the argument of the q function, look up in the q table, use the MATLAB program that I've given you to calculate q evaluated at x naught minus m over sigma, subtract that from 1, and you'll have the cumulative distribution function for a general Gaussian probability density function evaluated at x naught. Okay? One observation before I move on is that notice that by symmetry, you'll notice that q of minus x naught prime, using the notation of this figure, equals 1 minus q of x naught prime. All right? By symmetry. So if you happen to need to know the q function evaluated at a negative number, if the argument of your q function happens to be a negative number, just look up the q function evaluated at the positive value and subtract that from 1, and you've got your answer. So by symmetry, we can the q function tables are in your textbook are tabulated only for positive values, but by symmetry I can get access to the negative values, not negative values of the q function, but I can get values of the q function for negative arguments by symmetry. Okay? All right. So this is more or less, well, it's exactly what the cumulative distribution function for a zero mean, unit variance, Gaussian probability density function would look like. All right, this is the cumulative distribution function for the zero mean unit variance Gaussian random variable. You'll notice here that my cumulative distribution function is just 1 minus q of x in this particular case. All right, my cumulative distribution function in general equals 1 minus q of x minus m over sigma. But if m equals 0 and sigma equals 1, I just get that relationship. I use the MATLAB function q dot m to do the calculations for me. All right. You'll notice my function, my cumulative distribution function approaches unity at infinity. It approaches 0 at minus infinity. All right. It's an always non-decreasing function of the argument. All right. It's continuous, moving from the right to the left. All those kinds of things. It obeys all the proper properties of the cumulative distribution function. The only thing that would change if the mean was non-zero and the variance was not 1 is the curve would move to the right or to the left depending upon the mean, and the slope would change, either be steeper or shallower depending upon sigma. But in all cases it would approach 0 at minus infinity and 1 at plus infinity. All right. Let's now look at some alternate forms. 3. The first one is an interesting relationship that I believe is unique to the Cooper and McGillem textbook. They define a capital phi of x function, and it looks like this. Integral from minus infinity to x 1 over square root of 2 pi e to the minus u squared over 2 du. All right. By looking at the previous q function, we can see that this is simply 1 minus q of x. That's just 1 minus q of x. All right. The phi function is the integral of the lower tail. The integrand here, by the way, let me point out again that the integrand here is 0 mean, unit variance. All right. The q function is also involves an integral over a 0 mean unit variance Gaussian probability density function. The q function involves an integration over the upper tail. And phi, this one, involves an integration over lower tail. And since all Gaussian probability density functions, regardless of mean and variance, have area of 1, this has unit area, even though it is a 0 mean unit variance Gaussian PDF, it still has unit area. For that reason, integral over the lower tail has to equal 1 minus the integral over the upper tail. It's just that simple. For that reason, it should be relatively clear that the cumulative distribution function for a general Gaussian probability density function is just this. It's just that. Remember, from the q function, it's 1 minus q of x naught minus m over sigma. All right? And this is for a general. That's for a general Gaussian. Okay? So if we're trying to find the cumulative distribution function for a general Gaussian evaluated at some point x naught, I can use either the phi function or the q function. By the way, where is phi? The phi function is in Appendix D of your textbook of Cooper and McGillem. See. Phi of x is tabulated in Appendix D of Cooper and McGillem 3rd edition. The q function is tabulated in Appendix E of Cooper and McGillem. On tests, I will be giving you copies of those tables. You clearly won't have access to MATLAB, and most of you won't have q functions built into your calculators. So I'll provide for you tables to use on tests. Make sure you know how to read and interpret them. All right. Like I said, this phi function seems to be unique to Cooper and McGillem's textbook. I'd never seen it before I read through Cooper and McGillem. You will, however, from time to time run into things known as the complementary error function and the error function. So let's look at the error function first. ERF of x is the error function. All right, it's defined this way mathematically. It is defined in its most typical definition is given this way: 2 over square root of pi integral from 0 to x e to the minus u squared du. By symmetry, we can write this also as 1 over square root of pi integral from minus x to x e to the minus u squared du. All right. If I move my 1 over square root of pi inside of my integral, what I find is the integrand is a zero mean Gaussian PDF with a variance equal to 1/2. That's fine. Earlier we were talking about zero mean unit variance Gaussians when we were talking about the Q function and the phi function. Now the error function is described using a zero mean Gaussian probability density function with the variance equal to 1/2. That's fine. The area under such a curve is still going to be unity because the area under any Gaussian probability density function is 1 regardless of the mean and or the variance. So let's draw a curve for what this might look like. All right, this is my zero mean Gaussian with a variance of 1/2. It's zero mean, so it's going to be sitting here centered right at the origin. That's there. And let's call this point x0 and call that point minus x0. All right. The total area under this curve is 1. The area under that curve is exactly 1, as it is for any proper probability density function. My standard deviation is 1 over square root of 2. Now, if I then integrate from minus x0 up to x0, if I integrate from minus x0 up to x0, I calculate the error function evaluated at x0. So this red hatched area is the error function evaluated at x0. Okay? ERF of x0. We'll talk a little bit more about the complementary error function in just a minute, but let me just sketch out. The complementary error function is everything else. All right? The area under the upper and lower tails together is the complementary error function, designated by ERF-C. So this will be half ERF-C of x naught, and down here I'll also get 1/2 ERF-C of x naught. There. And in all cases, we'll have some more to say about this in just a minute. ERF-C of x naught is 1 minus error function at x naught. Okay? ERF-C equals 1 minus ERF. Okay? All right. So, how does this relate to the Q function and the ultimate cumulative distribution function for a general Gaussian? What's the relationship of the error function to the Q function? All right. The error function, recall, is 1 over square root of pi, integral from minus x to x, e to minus u squared du. This can be written as 1 minus, this integral is the area under the middle region, excuse me, from minus x up to x. By symmetry, this is 1 minus 2 times 1 over square root of pi, integral from x to infinity, e to the minus u squared du. So I'm subtracting from 1 2 times the integral over the upper region. And remember, an integral over an upper tail of a certain Gaussian is a Q function. So we're going to do some change of variables here and put this in the form of a Q function. So I'm going to let u equal, sorry for all the extra variables here, u equal w over square root of 2, and du equal dw over square root of 2. And after my change of variables, I get I get 1 minus 2 times 1 over square root of 2 pi, integral from x times the square root of 2 up to infinity, e to the minus w squared over 2 dw. All right. The lower limit on this integral is x times the square root of 2. All right. Now, if I take this 1 over square root of 2 pi and put it inside of my integrand, inside of my integral rather, my integrand is a zero mean unit variance Gaussian at this point. Okay, if I plug that 1 over square root of 2 pi inside of my integral, I get a zero mean unit variance Gaussian integrand. Well, when I integrate a zero mean unit variance Gaussian function, I get the Q function. So error function, one more step, your f of x equals 1 minus 2 Q function evaluated at x times square root of 2. That's that. Okay. I need to invert that a little bit. Or the Q function, rearranging just a bit, the Q function of x can be written as 1/2 1 minus error function of x divided by square root of 2. That's the form we need. Okay? That's the form we need. I promised that there would be 3 formulations for the Q function, and the third one has to do with the complementary error function that I alluded to earlier, ERFC. This is the complementary error function. Complementary error function. All right. Complementary error function, and the ERFC function is 1 minus error function. All right. So by looking at my relationship at the top of this page, I can see very clearly that the Q function is 1/2 ERFC of x divided by square root of 2. All right? That's the relationship we need. All right. Interestingly enough, the error function, I should make a note of this, in MATLAB, we have the following built-in functions. There is ERF.m, that's a built-in function. ERFC, the complementary error function, is built into MATLAB. ERFINV.m is also built into MATLAB. This is the inverse error function. All right? I have sent you, or will send you, Q.m, a MATLAB function to calculate the Q function directly, and Q inverse.m. All right? Okay. So let's just do a quick summary here of the various ways of calculating the cumulative distribution function for a general Gaussian. I'm having a hard time making Y's today. Summary. The cumulative distribution function for a general Gaussian evaluated at x naught is 1 minus Q of x naught minus m over sigma. You can rewrite this as 1 minus Q of x naught prime, where x naught prime equals x naught minus m over sigma. All right, I have three different ways that I can calculate the Q function if I don't just directly calculate Q using tables or the Q.M MATLAB function. Q of x naught prime can be written this way: 1 minus this capital phi of x naught prime. That's one way, using the Q function, using the capital phi function. It can also be written as 1/2 times the complementary error function, evaluated at x naught prime over square root of 2. And can also be written using the regular error function, 1/2 times 1 minus ERF of x naught prime over square root of 2. Okay? So, if you want to calculate the cumulative distribution function for a general Gaussian probability density function, so keep in mind this is for a general Gaussian. You've got several ways to do it. MATLAB's got the error function built in and the complementary error function built in. I've sent you programs for calculating Q functions. Later on we'll need the inverse Q function. Use what you have to calculate what you need. That's all I have to talk about today. As usual, if you have any questions, please do let me know at your earliest convenience, and I will do my very best to answer all your questions fully and completely. Have a great day. Bye-bye.